Good afternoon, everybody, and welcome along to this Open Source Satellite Programme meetup session, the first one we've had for a little while, so it's really nice to get these sessions going again. So I've got the great pleasure of introducing Dr. John Paffett, the Managing Director of KISPE, who's going to talk about the programme and why it's important and what we aim to get out of it. So I'm going to hand over straight to John.
Thanks, Catherine, and welcome everybody. Good afternoon, good evening, good morning, wherever you are. It's great to have so many people online. As Catherine said, we've had a bit of a downtime over the summer, or not a downtime. We've actually been very busy, but it's been quite hectic over the summer period. So we thought we'd restart the Open Source Satellites programme of activities. I thought the good way to start actually would be just to give it a bit of an overview of the programme and why we're doing it. So what I plan to do then is do a little bit of an introduction basically to myself and the company and what we're doing, a bit of the motivation, why we decided to move forwards with the development of the next generation microsatellite platform, and why we're big fans for things like the open source approach. So talk about our motivation for why we're developing and going to release into the wild a high performance 25 to 250 kilo microsatellite platform. So we'll talk through that. I also want to talk a little bit about our approach to open source. One of the things that I've become aware of over time is that the term open source and collaboration can mean different things to different people. So we'll talk a bit about that. I'll then go through the next generation microsatellite platform, and then also talk about some of the other things that we're doing as well, some of the other open source related activities that we've been involved in, and we're progressing and hoping to release out into the public shortly. And then I'll leave a bit of time at the end for discussion if anybody's got any questions. So by way of introduction then, as Catherine said, I'm John Paffett. I'm the founder and managing director of KISPE, and I like to think about myself as sort of the chief architect and evangelist for the open source satellite program. My background is I've been involved in small satellite missions for the last 30 plus years in a range of different companies and organizations. So built upwards of 50 spacecraft over the last 3 decades. So, as I mentioned, I set up a company called KISPE. We're a program and systems engineering company, and you know, really, people often ask me, you know, what do we do? Well, we're really driven by the desire to make space more accessible. So, all about stimulating the utility and application. And really promoting the responsible and sustainable use of space. When I first started building small spacecraft, people looked at us and thought it was a bit of a joke and said, you can't do anything useful with a small spacecraft. And certainly for the first 15 years of my career, we faced quite an interesting challenge to demonstrate to people that you could really do useful things. You know, now very much vindicated. There's not a day that doesn't go by without reading of somebody looking to do some new application or service that's delivered by a small satellite platform. So you know, that's really the heart of what we try to do as an organization, as a company. And we work with a range of different clients across the board, helping them take their initial ideas and sort of turn them into a reality. So as a company, we cover quite a spectrum of activities, working from training and workforce development through mission and system design, through provision of specialist space support, strategic business and program support. We design and build and manufacture space-related electronics and subsystems. We're involved in the design and manufacture of spacecraft, and on occasions we'll build spacecraft. So we've got a small marine environmental monitoring spacecraft that's going through the building at the moment, through the clean room at the moment, which is for a program with Cornwall Council looking at marine environmental monitoring. So quite a spectrum of activities, but again, it's all driven by that desire to try and stimulate the use and application of space and make space more accessible. So running a company, you go, well, why on earth are you looking at developing a small satellite platform, and then why are you looking at making that open source? So, as I mentioned earlier, there's not a day goes by that we're not seeing some report of a new application service. Space is taking an increasingly important role in all of our lives. One of the challenges is actually to make people aware of the importance of space and the role that space plays. So that's whether it's using spacecraft for doing Earth observation, or whether we're using spacecraft for communications, or whether we're looking out at the stars, or whether we're using satellites for precision navigation and timing. There's a range of different applications that we're using space, and saying it's becoming increasingly more important as it becomes a more intrinsic part of how we operate. In fact, I think if you were to turn off spacecraft for a 24-hour period, a lot of the things that we're used to would just come to a grinding halt. I mean, we're now trying to get so much efficiency out of things like our utility services, electricity and water, that I think if you turned off navigation, and in particular turn off the timing signal of navigation, a lot of that infrastructure would just come to a grinding halt, because there's nothing providing as accuracy in the clock and in the synchronization of those activities. We're dependent upon navigation. And so many people now, as they get into their cars in the morning and are off to visit a particular location, don't even have a map. They just put the location into their car and blindly follow the GPS. They get very lost if we were without navigation. So the number of applications, the number of uses of space is increasing at a phenomenal rate. And what's driving that growth? And there's a number of things driving that growth, really. It's being driven by advances in technology. So, we're able to do more and more and more in small volumes and small packages. The instrumentation is improving. The capabilities of computers are improving. The capabilities of instruments are improving. The amount of data we can store is improving. So we're getting these increases in technological capability. We're also getting a reduction in cost, and whether that's a reduction in launch price or a reduction in the price of satellite platforms, all of that is helping to fuel that growth, fuel that demand. We also have an improvement in accessibility. So the number of launch opportunities to get spacecraft into orbit is increasing. We're not quite there yet in terms of having excess supply, and there's lots of talk about a lot of different launcher developments and how the market's going to be saturated. For any of you that are trying to buy launches today, actually it's quite difficult. The SpaceX is a large provider of launch capability. Outside of that, at the moment, there are only a few other players like Rocket Labs and the Indians with the PSLV. But accessibility is still a challenge, but it is improving. And then, as I mentioned, the increased utility in application. So, as I mentioned, back in the early days when I was with Surrey and we were putting up small 50 kilo microsatellites, people would look at them and say, what useful thing can you do with a spacecraft of that size? Now, with advances in camera technology, for example, we can be doing a whole range of Earth observation missions, or with the communications payload, the communications missions. So that utility is continuing to grow, and you see that in the increase in the number of satellites that have been launched and continue to be launched. Now, these figures to some extent are distorted by the deployment of some of the mega constellations, so Starlink or OneWeb and others. But what you are seeing underneath of that is irrespective, is a growth in the number of spacecraft that are being launched, and that will continue to grow. Now, the challenge, though, is the cost, and I'll come back a little bit to cost in a minute. But if we think back to the very beginning of the use and application of space and the launch of some of the early spacecraft, I'm going to try to shy away from the term small satellite at this point, because some of those early spacecraft were relatively small in size. But one of the factors was they were very expensive. So the early or conventional spacecraft were expensive, were very much to preserve of a small number of spacefaring nations. So, you look back and the US and Russia very much the pioneers, the use of space. Then you start to see other countries that are launching space assets. But it was very much an exclusive environment for the superpowers. It was only when the likes of companies such as Surrey Satellite Technology and Orbital Sciences in the US, they took a different approach to space-based missions. So using, for example, commercial off-the-shelf components, commercial off-shelf processes, they were able to radically reduce the price performance point of small spacecraft. And that started making space more accessible. In fact, back in the early days, Surrey's tagline at the time was affordable access to space, because we were able to provide small spacecraft that enabled other non-superpowers to have access to space, whether they were countries, the likes of Thailand and Malaysia and Chile, or whether they were commercial companies. It started to open up space for more. So the microsatellites, they played a significant role in making space more accessible and opening up the market to more parties. And then came along the CubeSat development. So Geordie, Roland, the team out in the US, for example, developing the CubeSat initially with a view of using the CubeSat as a training tool for further education and university training. But it very quickly got traction. You know, this idea of having a small spacecraft at a fraction of the price of the microsatellites really helped to reduce the entry barrier costs, you know, making space, you know, I'd say accessible to all. You know, you still have a price tag of several £100,000 for some of those missions, but it does make space a lot more accessible. So what you've seen is some significant improvements, and also significant step changes in the price performance point of spacecraft, and also the ability to open up the space market to other players and other actors. You've got to be very careful, and this is a point that I have to make to a lot of people. You're not comparing like for like. So while significant progress has been made in reducing the price point of some of those spacecraft solutions, that typically comes at the expense of performance or capability or reliability. So if you just think about an Earth observation spacecraft and you look at a digital eye or worldview spacecraft, you look at a Surrey Earth observation spacecraft and you look at a Planet Cube satellite, for example, you can go, oh, they all take images, fine. But the performance and the capability of those spacecraft is vastly different. So there's a certain element of you get what you pay for. And so, you know, some of the lower cost missions are very, very basic, very constrained. As you move up in size, the price will increase, but you get a bit more performance. And then if budget's not your issue, you can buy the biggest, the best spacecraft and you'll pay for it, but you get all the bells and all the whistles and it's nicely wrapped up in a bow, you know, that. So there's a certain element of getting what you pay for, as it were. But the good thing about it is it has opened up the market and made space a lot more accessible to others. The biggest challenge, though, with space programs, well, several challenges actually, but fundamentally, the costs are too high, the development schedules are too long, and the lifetime is too short. So this is a classic, what I call S-curve. So this is a plot of cost over time. And you do this for any business. You work out what it's going to cost you. You work out when you start to make some income or revenues, and it would classically follow an S-curve. The business development people will be overly optimistic, so they'll assume that this is going to make a lot more money a lot more quickly, and very seldomly does. And then sometimes systems, you know, just do not come to fruition, and you know, the outcome is that they don't succeed, they fail, they never break even. And so those issues around cost and about development time are really key. That development time is costing us because we've raised that money, we're having to pay interest on money, for example. Then when we find that we've deployed these spacecraft, you're effectively on a ticking asset. So you've got a spacecraft with a limited lifetime. You need to be getting revenues from that spacecraft as soon and as quickly as possible. If it takes a long time to bring customers on board, then you may not find that you get enough income in order to make the program viable. So it's a constant challenge. And so, we're routinely working with customers with some great ideas, but one of the challenges they've got is how do they actually close the business case? How can they get a solution at the right price within the right time scale that has a long enough life in order for them to actually be able to generate the revenues and repay the system? And so that's just, a fundamental issue of space-based programs. One of the other issues that we have is, and this is not me beating up on CubeSats. Actually, there's great innovation that's happening across that spectrum of capability. But one of the problems I'm often seeing now is I'm seeing customers go, I need a 3U CubeSat. And you go, what are you talking about? Actually, you need a satellite that does the job you need it to do. The size of the satellite is a consequence. But the problem is people get attracted by price and say, actually, I'm going to pick the cheapest. And one of the problems you start to find is quite often that may not be the best solution for the problem or the mission that needs to be delivered. And so, you could do a lot of really good things in small spacecraft, but you can't break the laws of physics. So things will always be resource constrained. So whether that's the amount of power that we can generate, or the amount of temperature that we can dissipate, or the amount of battery storage on board, or the amount that we can physically fit in the box. So we often see customers that are very financially constrained, trying to get their missions off the ground, are trying to squeeze too much into a small pot, and it ends up sort of bulging out the side. So it's quite an interesting challenge. So the sorts of trends we're seeing as a result of that, we're seeing the microsatellite vendors trying to come down in price whilst maintain performance. They're also trying to increase performance as well, but you can see that they're trying to bring things down to help close more of those business cases. We're seeing the CubeSat vendors looking to increase the size and performance of some of their spacecraft. Quite often at the moment, though, what we're seeing is those being CubeSat avionics, but in larger boxes. So we'll see somebody going, well, we can provide you with a 16U, 12U CubeSat, for example, and actually fundamentally the avionics is similar. It's just in a bigger box with larger solar panels. So it starts to inherit some of the issues from previously. Maybe there's a bit more accommodation space because of the larger satellite platform, but you're still struggling to meet the performance requirements of some of those missions. And so what we're seeing is some of the missions are going unserved or unmet or unaddressed. When we started looking at this, we then went, actually, what the market needs is just something very different. If I look at the traditional spacecraft, I look at what the microsatellites have done, and I look at what the CubeSats are doing, and I look at the trends of where those different actors or vendors are trying to develop products, they all seem to be on the same line. And none of them are jumping off and going, we need to do something different. And this was one of the motivations for the next generation microsatellite platform, was to go, actually, we can't carry on doing the same as everybody else is doing. We need to step off that line and do something different. How do we get to a high performance, low cost microsatellite platform? I get a bit annoyed when I'm at a conference and I hear people say, I only need a spacecraft to last for a year. What they really mean is they can only afford one that lasts a year. We'd be so much better off if we're putting up spacecraft with a lot more redundant robustness and reliability with longer lifetime. That gives several reasons for that. It gives more surety of the business. It gives us more time to demonstrate and experiment with technologies. It gives a bit more robustness to provision of services. But sometimes if budgets are constrained, you are driven to making compromises, and whether that's in technical performance or robustness and reliability or over just lifetime. And so that was one of the motivations for the program, is to say the market needs something different. And when we look at a classical microsatellite platform and you look at where the costs are in that platform, so much of it is to do with labor. And so we went, okay, what have we learned over the last 30 years? And how can we apply that to the development of a next gen platform? And a lot of that is about engineering discipline and taking a different approach in terms of how we do the manufacture, so that we can drive the recurrent price of the platform down without sacrificing performance or capability. So that was very much the genesis of what led us to what I call the development of the next generation satellite platform. The other element, though, and this is where the open source piece comes in, is we as a company, KISPE as a company, myself, are very much about trying to stimulate the use and application of space. In fact, it's one of the reasons why I went and worked with Surrey in the first place. It was off the back of a very interesting talk that Sir Martin Sweeting did, talking about how we could make space more accessible to a range of people who could not get access to space-based capabilities. And you go, yes, I believe in that. We can make space more accessible. So as a company, we're not trying to be another manufacturer, but what we've identified is the fact there's a capability that's missing. And also there's a lot we can do to help stimulate and drive the market. And so we thought, well, if we need to develop this satellite platform to address a market need, we can do that. But could we just take a different approach rather than going IP and hold on to that IP and defend it fiercely? Could we not take a leaf from other industries, other sectors, and take a different approach? And that's where we came from, with the idea of we'll develop the platform, and then one of the routes to market we'll take is to make that platform available through the open source licensing. So basically make space more accessible through the development of an open source microsatellite platform and a broader community. So that was the whole genesis behind the open source satellite program, was to go, we can develop a next gen platform, we can develop space related capabilities, and actually let's make some of that available to the community through the open source regime so that people can build upon that and not have to reinvent the wheel. I'm very much a techie at the end of the day. I mean, I've got an engineering background. I love designing and building things. Electronics and the software has changed massively over the last 30 years through things like the internet and the repositories of information and tutorials and open source design. So you're not having to start from scratch in designing a new circuit or a new piece of software. There's plenty of reference source material out there that can be used, and that makes the whole process a lot more efficient. And it means that rather than constantly reinventing the wheel, we can build upon things and we can do more and more and more. And so again, that was really the genesis of what we were trying to achieve when we set the program up initially. And so our vision then was very much around making space more accessible. So how do we do that? What can we do to make space accessible? And so our mission: stimulate the utilization, exploitation of new applications, new services, to promote the useful, the responsible, sustainable use of space. So that's really what we're trying to do through the program. But also the other thing I'm very, very conscious about is making that information, the design information, openly and freely available. Now for the platform stuff, we're going to be releasing it as we go along, and then make sure the entire design is released once we've launched the spacecraft and that we've got the heritage. But get the information out there and get the information out there for perpetuity. One of my big bugbears with some of the previous open source programs is programs will start off and come back 5 years later and try to find the information and it's evaporated. You can't find the material, or you have to be a GitHub ninja because it's buried away somewhere deep in the depths of a GitHub site. So how can we make that information more accessible? How can we make that information more available? And how can we make sure that information's there so people can take it and use it in the future? And so we've been giving a lot of thought about how we do that. And that again is where we came from in development of the open source satellite program and then the open source satellite website. So that's really part of the motivation for what we were trying to achieve there. Now, so that was the sort of the why. So I mean, from a simplistic view, it's very much because there's a market need for high performance, low cost spacecraft that have a long lifetime and high reliability and robustness. But but also we need to be able to find a way of stimulating the market. So yeah, let's make that platform capability open source and to stimulate the market. Now, I mentioned at the very beginning, when you start using terms like open source and collaboration and tools and development, it means different things to different people. There's a number of different groups around the world that are all doing open source related activities, and it's fabulous. And in my view, there's no one way of doing things. It's each to their own. The way that we look at open source is in a similar way that Spark, Fun and Adafruit, and for any of you that are not aware of either of those companies, they make electronic breakout boards for hobbyist makers and others, and even Raspberry Pi to some extent is very similar, where they will develop and they will get the material to a level of maturity, and they may develop things either internally or through collaborations. But once it's reached a releasable point, then they will release it out into the wild through a open source licensing regime. And we're adopting the same approach. So we've got a lot of developments on the go at the moment that are not quite there yet, that aren't out in the wild. And why is because I want to make sure that when we do release things, we release things that are, you know, in a very solid starting point, are very well documented, and actually provide a good foundation for people to build upon. You know, there's nothing worse than picking up on somebody else's work, spending months trying to, you know, believing that it's going to do something, and then find that it doesn't work, or the documentation is somewhat limited. So that's a key element for us as well to get that done. So again, that model that we're using is development and release. And so what are we doing? We're developing a 25 to 250 kilo high performance microsatellite platform, and I'll say other related material, and I'll come back to a bit of that later. And then as we go through, we will be releasing that to the community as we complete elements. So as they're completed, as they're documented, then we will release them out. Our way that we release them is, say, under an open source license. So material will be released under some open source licensing, or not under some, under our open source licensing regime, in a well documented, clear and transparent way. The reason why I'm saying both of those is I've had a number of discussions with people in the past that are saying, well, if it's open source, you should be throwing out a blank paper design and crowdsourcing the development. That's not the approach we're taking. You know, the approach we're taking is to say, okay, we will work with parties, we'll work with collaborators, which I'll come back to in a minute, but we will develop that together or internally, and then we'll release, and then we can build upon things in the future. So that gives a nice solid foundation layer that we can build upon. So as I mentioned, from a development perspective, we're developing this internally, some of it purely on our own, some of it with collaborators, some of it with partners. So it's not a blank sheet or crowdsourced design activity. Those developments take place within teams, and then we release them when we're completed. And we've invested just over 2.4 million so far in the development of this activity. And so as we're doing commercial programs and others, I will continually to reinvest some of the money that we make from those programs into this development, to move this development forwards, because, you know, it's one of the things that we're passionate about. In terms of collaborators, so we welcome collaborators and partners to help us on that journey, as it were, and really to help us create the materials that benefit to the community. So there's a couple of projects I'm going to talk about later that are not purely related to the 25 to 250 kilo class platform, but they are things that we think people will be interested in and would like to use or like to take and develop further. So we've said, well, actually, that's a worthwhile thing to do. So let's do that and get that out into the community. Another point that will sometimes come up is around the use of tools. I had a discussion with somebody a while ago who, well, they didn't like our develop and release approach, and they didn't like the fact that we were only using pure open source tools, which I thought was ironic given that they had an Apple Mac. But anyway, but so from a tool perspective, you know, development of the platform is a challenge in itself. And so as we're going forward, we do try to use open source tools and tool chains where they exist. But we're also trying not to handicap ourselves in any way either. So in reality, what we do is we try to make use of the best tools that are available to us. And I say available to us, there's a number of things we'd love to use, but we just don't have the funding to be able to buy them. But yeah, we try to make use of the best tools to do the job that we need to do, but always with an eye on the fact that we want to release the information and make the information available to the community so the community can take it and build upon it. And I say that's no different than the likes of SparkFun and Adafruit and Raspberry Pi, or even Lime Micro. You know, those different groups will use different sets of tools. You know, some will use Eagle as the electronics design schematics PCB tool. Others are using other packages. But the core thing really is getting that end design product, the design knowledge out there to people. So I just thought I would touch on the approach, because I say that sometimes means different things to different people. In terms of the platform then, so this is the big part of of what we've been doing, and I will confess this is taking us a lot longer than I was originally planning. And part of it is not the technical content. Actually, part of it is trying to raise the money to do the development and to fund the activities. This is going to sound a bit stupid, but you know, CubeSats are low cost, but they're not designed to be low cost, as it were. They're low cost intrinsically because they use low cost components. What we're trying to do with the bigger platform is really drive that price point down by removing labor or reducing labor considerably, by also looking at how we can design this to make them very much lower cost. So we've got an activity ongoing, or had an activity ongoing earlier last year, looking at things like the separation system. And people say to me, well, why are you looking at the separation system? You can go buy them. And you go, yeah, but if I want to get a 100 kilo or 50 kilo class platform and get that down to the price point of about $1 million, I can't afford to be spending $100,000 or $150,000 on a separation system. So how do you do all the NRE we need to do in order to drive that recurrent price point down? And so actually the development is very non-recurrent engineering intensive, so capital intensive for the development, in order to really drive that price point of the satellite down. So the open source satellite is being designed to address that gap in the market, and that is the need for high performance, robust, reliable microsatellite platforms, but at the price point or close to the price point of a CubeSat. So that's really what's driving us, and not going, it's a 32U, it's moving away from that to go, no, it's not driven by that sort of form factor. It's driven by the fact that we need something that is versatile, it's scalable, that we can take and cover a range of different sizes of missions from about 25 to 250 kilos. And what we ultimately want to do in the future is get to a point where we have a solution that is suitable for harsh and benign environments. So benign, I'm meaning sort of the low Earth orbit environment, and by harsh environments, I'm meaning MEO, GEO, lunar and beyond. We're certainly not going to get there in one foul step. You know, if I try to simplistically explain what we're trying to do with the microsat development, is we're trying to shrink as much of the core avionics into a tiny box that's not going to change. You know, we'll get a 70% solution for that for the first mission potentially. But you know, what I'd like to do in the future is take that even further, and you know, can I shrink that onto a chipset, for example? Can I get that onto an intrinsically rad tolerant chipset that then can be used on a range of different missions? You know, we won't get there in one foul swoop. We're trying to break that down into a number of paths or a number of steps. Thinking of, you know, we're trying to conquer a mountain, how to break that down into bite-sized chunks, as it were. So 25 to 250 kilos, versatile and scalable, but thinking about the robustness, the resilience, and lifetime. Again, trying to encourage us not to be deploying spacecraft with a finite lifetime, or a very short lifetime, trying to encourage us to be thinking about things like debris, collision avoidance, re-entry. Can we ensure that we have enough propulsion on board the spacecraft so that we can deorbit the spacecraft not within 25 years, which is the current sort of guidelines, but in a much reduced period of time. But also recognizing that the missions will change and adapt over time. So actually, can we have a scalable architecture that enables us to put other subsystems and equipments on to be able to have a higher performance power system, propulsion system, for example? So taking all of those elements into account. So the sort of spec or performance of this first generation of the platform that we're looking at, say it's something between the 25 to 250 kilos, and trying to get to a point of about a 70% payload fraction. Now that clearly is not on the 25 kilo platform. That's at the larger end of the spacecraft. But that sort of thing, thinking about the flexibility of the payload accommodation. One thing I've learned from being in this business for a long time and working with a lot of different customers is we worked with one space agency for many years who did a lot of study work trying to envelope all of the missions that they were ever going to likely do to come up with the design of their microsatellite platform. And then the first one that they actually had to do didn't fit within that envelope. So you almost have to step back and go, let's just acknowledge that spacecraft need to be driven by payload. Payloads will change, and actually we need an effective way for the platforms to be able to adapt and change and evolve with them. And thinking about how we do the non-recurrent engineering in a way that reduces those costs or minimize those costs, acknowledging that those costs will be there. I've had a number of people talk to me and say, John, you're mad. Spacecraft are now commoditized. Why are you bothering? Because there's companies like OneWeb that are putting these spacecraft off of the production line at a rate of knots. That's great if you want a OneWeb type of spacecraft and you're building it at the same time as everybody as they're building all the other ones. But if you've got a bespoke mission that needs to do a specific thing, do you really need something that big, or do you need to wait until it's available, or do you have to pay the NRE to do what you actually need to do? If that logic was correct, there would only be one car manufacturer and there'd only be one aircraft manufacturer, and clearly that's not the case. So flexible payload accommodations, scalable power, acknowledging that different payloads, different missions are going to have different payload requirements and power requirements. So, seeing if we're looking at a 25 to 250 kilo platform, then we know that the number of different payload variants for that type of mission is quite vast. It could be anything from a 10-watt payload up to a kilowatt type of payload. So how do we scale that? We know that the majority of the missions that we're looking at need to be 3-axis stabilized with a fair degree of pointing accuracy. We know for this first iteration that we're looking at predominantly orbits between about 400 and 850 kilometers. Again, in the future, we're looking at how to then expand that into other orbits. Simplicity over things like S-band TTC, generic payload interfaces, open interfaces for higher performance subsystems. Really thinking about trying to keep these things, crisp and clean, and keeping clear delineation between platform and payload. And that architecture piece is also really, really important. I just look back over the last, say, 50 missions, and I think in some instances we would be much better off if we'd had a very, very clear delineation between what is the platform and what is the payload. And we don't need to keep on changing the platform for the sake of changing the platform. Why don't we just lock that down, have that as a core design, and then spend all of our attention on the payload and the mission? Because at the end of the day, all the platform is there to do is hold our payload in orbit and provide the resources that it needs to do the job. The fact it's got a particular OBC, whilst that might sound really sexy and exciting, that's not the mission defining function. The mission defining function is what it does. So let's try to park the platform, get the platform mature and done. Don't touch it, don't change it, and just focus on what the mission needs to do. And again, recognizing the fact that we need an architecture that can support the inclusion of additional sensors and actuators. So we may have a mission that needs to off point at a rapid pace, for example, and so we may need bigger wheels. We may need a higher precision for the pointing performance. So we may need higher performance star trackers, for example. Now, if we were to build those all into the baseline offering, then you end up with a cost point that's way too expensive for some of the simpler payloads. So it's just trying to come up with I hate the term, a minimum viable product that gives you a high performance solution, but an architecture that enables you to sort of add onto it and bolt onto it. So and we've been doing a lot of work on that with the idea of this core. So the open source satellite integrated platform avionics unit is the core. Those are the elements that really do not change on a mission by mission basis. And so we've been doing a lot of work on that area, on trying to start to finalize the design of that, prototype up elements, move forwards. So where are we? So on the requirements and the architecture side of things, we've now established a clear baseline, and that gives us a good solid foundation for what we're going to do on the hardware development activities. We've been doing a lot on the software side, and in fact we're looking to use the software on the mission that we're doing with Cornwall for KERNOSAT 1. So that's progressing towards a first flight, which is likely to be Q3 next year. I'm trying to get the mission so that it's actually finished off by about April next year. So things like the bootloader, it's ongoing development, nearly complete. The real-time operating system that we're using, that's also nearly complete. So as soon as we've got those done, we're going to be releasing those into the community. The application software, ongoing development, but that's making good progress as well. For KERNOSAT, it's not actually our AOCS algorithms. So for that particular mission, there's an AOCS unit that we're using, but we'll be moving forwards with our own AOCS algorithms and releasing those as well. There's a couple of what I'd call side projects that have come out of this as well. So CCSDS for the communications link between the satellite and the ground. You know, this is supposedly a standard. I'd say the one thing it's not is it's not a consistently implemented standard. Different groups have implemented it slightly differently, and certainly my experience of the past is you'll get people going, yeah, we're CCSDS. And if you don't dig down a little bit deeper, you start running into problems because the ground equipment doesn't compatible with the spacecraft equipment, because actually the implementations are slightly different. So one of the things that we thought about was to say, okay, how can you standardize the standard? And we thought, well, actually, if we release an open source implementation of CCSDS, that gives people a starting point to start from, and hopefully that will start to drive some form of standardization. So that software is complete. We're just finalizing the documentation things at the moment prior to release. Another thing that we're working moving forwards on is with the CAN. So this is the control area network. So this is the bus that we use to connect a number of our sensors and actuators within the spacecraft. That work's been ongoing and is near complete, and we'll be releasing that out shortly as well. On the hardware side, our focus for the last couple of months has been very much on the platform side of things. That core processor capability will form the heart of the integrated platform avionics unit. So on the platform processor side, we've completed some radiation testing, selected the devices. We've actually generated an engineering model on board computer development platform, which was released out into the community through our GitHub site last year or beginning of this year. I will, once we're through the global chip shortages, where once we've got some more of the STM32 devices, we'll probably make up some of those boards and have them available for anybody that wants to be doing software development and using the OBC. But that will form the heart of our integrated payload avionics unit. So that's sort of in a bit of a whirlwind where we are with the platform. But I thought it was also worth just touching upon some of the other open source releases and other related activities. So some of you might be aware we did a piece of work with some collaborators a while ago on what we call Mercury GS, and this was the desire to basically have a small program that enables us to interact with the spacecraft and lab environment. So this was Mercury GS. That was released back in 20, I think it was end of 21. So I know a couple of people have taken that and have moved forwards with that as well. The OSSAT OBC development board, so again, that's on GitHub. And that's the full design, the build, the test information for what is the development board computer. So both of those things you can see on and find on GitHub today. We've got a number of other things that are working through and in varying stages of development. And as these become final, we will be releasing them through GitHub as well. So that's the CCSDS implementation that I mentioned earlier. Really in the process now of just getting that written up so we can get it on there. The control area CAN reference node, so that's the reference hardware node design, the protocol definition, the software source code. That's pretty much done. Just need to get that, say, finished off and released, but really looking to get that out early next year. And associated with that is CAN PC, although I know the guys aren't quite calling it that, but that's basically a CAN analyzer or piece of CAN analyzer software that we use for ground-based testing. So then we can hook the satellite up to a PC and interrogate the subsystems. We can send telecommands, receive telemetry, but we can also use it for things like stimulating the attitude control system. So we can actually send environmental information, as it were, so almost mimicking what the satellite would be like in orbit, so that the OCS system can respond to it. So I've seen a couple of demos of that from the team recently. Again, I think that's pretty much there, so hopefully we'll get that out shortly as well. So then there's other not quite platform related things, but related. So I did a talk, I think it was back in May, on the open source satellite sort of training model, as called it, OSSAT-T. If anybody's got a better name, that'd be brilliant. So what we're trying to do here is have a functionally representative satellite model that we can use for training for development, for training for education, but also for development. So basically have a payload interface that enables us to be using it with people who can then start developing payloads, which will then eventually be flown on things like the NGMP or the open source satellite. So we've been doing various pieces on this over the summer, from redesigning the power system and the RF subsystem, through to looking at what we do slightly differently on the AOCS side. So I'm hoping that we can make some better progress on that, with a view of getting that completed sort of the middle of next year. So that'd be good. We're going to be using that for teaching things like systems engineering and for really trying to get across a basic understanding of space, the uses of space and spacecraft engineering. Another thing that we've been involved in over the last few months, and this relates to the work that we're doing on KISPE and the flight operations of that spacecraft. We were looking at what is a good solution for the mission operations software. So we've been looking at and working on the use of YAMS. So this is a open source software framework that can be used for spacecraft operations. So the team there has done a great job. I'm hoping that we can actually get them on one of these calls in the future so they can talk about what they've done. But we've been doing a lot of work on this to configure YAMS so that it will work with the open source satellite. In fact, also have it work with the OSSAT-T as well. So that's moving forwards. So we have a configuration now that we're using for KISPE. That initial phase activity is completed. Again, we're going to move in the process of documenting and releasing. yeah, we've done a number of things here that I think that are going to be interesting to the community. So we've got an alternative spacecraft simulator that we developed to work with that, as well as the configuration and load files for how to use it with both OSSAT and OSSAT-T. And we've also been looking at a Raspberry Pi based implementation of YAMS as well. So that's particularly relevant for things like the OSSAT-T training spacecraft, where we wanted, something that is relatively inexpensive that we could be using for the ground station. So that seems to be working well. So look forward to getting those out into the wild over the next couple of months. So that was all I was planning to talk about. I thought I'd just open up the floor if there are any questions from anybody. Did I see Ben? I think you had your hand up.
Hey, yeah, thanks. This is really, really great. I've been following you guys for, I guess, a few years now. Nice to see an update. Do you have, I was wondering about like developing drivers or libraries for external hardware. So like, are you going to have I imagine there's probably 15 or 20 different mini electric propulsion companies now trying to develop stuff. I mean, currently, do you have like, a propulsion system that you could hook up to, or is there an intent to develop libraries for, various different pieces of ACS hardware or other hardware, comm hardware, anything?
Yeah, so that is one of the changes that we've made in the last, I'll say, year, 18 months, and partly driven by regulation as well, or where we think the regulation's going. So what we're going to try, or our plan for the baseline platform, is to build in a small propulsion system that's adequate for, let's call it an element of collision avoidance and re-entry. But we also recognize that many of the missions are likely to want to have higher performance propulsion systems. So one of the things that we've been doing a bit of work on over the last couple of months is how can we start to develop an interface and work with some prospective suppliers so that we can interface their propulsion systems easily into the platform in the future. And that's why I've been pushing with things like the release of the CAN interface, for example. CAN is another one where there's various different implementations. So if we can start to encourage people to use particular types of interfaces, then that makes the integration of some of those subsystems and equipments a lot easier. That's one of the things that we've found quite difficult on some of our other programs. And again, this is not beating up on CubeSats, but people talk about standards, but actually, different people have implemented things in different ways. So how can we start to encourage people to have more consistent interfaces? And so things like CAN is a good way of doing that. But again, also engagement with some of those suppliers. So understanding what those suppliers have got, and also working with them to say, how could we work with them so that they have interfaces that could be compatible with the platform in the future, if that makes sense.
Yeah, great, thank you.
John, we have had a couple of questions in the chat about how people could get involved.
Yeah, so we do say, as I mentioned earlier, we are working with a number of collaborators and partners on various elements of the development at the moment. If you go to the open source satellite website, we've got a mechanism there for collaborators to sort of reach out to us and let us know that they're interested. I'd say just bear with us a little bit as well. There's one of the challenges that we've got is just sort of trying to link some of the collaborators up with some of the developments that we're doing at the moment, as it were. But by all means, that's probably the best port of entry to try to get into contact with us.
Anybody else got any questions? Well, if not, thank you very much, John, for a really great overview of the programme. It's been an absolute pleasure to welcome so many people to the meeting this afternoon. So our next meeting will be Thursday, the 16th of November. John touched on the subject of CCSDS, so we're going to cover that and do a little bit of, oh, there's the slide we needed, John. So we're going to do CCS for Dummies. So that's the same time next month, a slightly different week, but it's Thursday, the 6th of November. Watch our social channels and for the release of that and the link for the Eventbrite. So that will be coming up soon. So, oh, there we go.
There you go. And I'd just like to say thank you to everybody for joining as well. I know it's sort of eating into your days at whatever part of the day it is. So thanks for your time and your patience, and hope you found the information interesting, and hope to be talking and working with some of you in the future. Thank you, Catherine.
Right.
That's good.
Thank you. Thank you, everybody.
Have a good day. Bye-bye.
Bye.